Welcome back everyone. In this lecture we will actually continue to understand the diagonal groups, okay, in more abstract way, and we will also determine all possible finite subgroups of this O of R2. Okay, so let's start with recalling what we proved in the last class. Okay, so if you start with this n gon, so which we interpreted as follows. So, if you take this n gon 1, 2, 3, n minus 1 n, this etc., then the symmetries of this n gon. So, this we call it n gon. The symmetries of this n gon is what we denoted by 2n. So, this is called the dihedral group, and we realize that this is explicitly given by these elements r power k, rho power L, where k ranges from 0 to n minus 1 and L ranges from 0 to 1, okay, where r power n is identity and rho power 2 is identity, and they satisfy this relation r rho equal to rho r inverse. So, this is what we verified for the dihedral group. So, in most of the books you can see that the dihedral groups are defined using what is called presentation of a group. Okay. So, to actually define a presentation we need to introduce what is called free group and quotient of free groups and so on. So, since we do not have time for all this, so I will just actually state a result that actually useful in order to get the presentation of this dihedral groups T2n. Okay, what is that result? Here is the theorem. You start with the group G. So, let G be a group. So, let us say G be a finite group. Okay, we do not need to worry about infinite groups, but we do not need to assume finite group. Okay, maybe we can just ignore this. We say that let G be a group. Okay, and let us say there exists A comma B in G such that G is generated by A comma B and A B both satisfies the relations that we have stated earlier. So, that means A power n is identity and B power 2 is identity and A B is same as B A inverse. Okay. So, G is generated by A B and modulo some relations. So, that is A power n is identity, B square is identity and A B equal to B A inverse. So, if all these things are true in the group G, so then we can claim that the order of the group can be at most only 2n. So, it can be only max the number of elements in G is 2n. So, let us see how one can prove this. So, now the proof is simple. Okay. So, now first use this identities and then see what you can tell about it. So, now A B equal to B A inverse, from this you can immediately say that A power k B is going to be exactly equal to B times A power minus k for all now k again from 0 to n minus 1, because when k is n then it is going to be just identity, there is nothing to check, and this is easy to prove, just to use induction to verify this. Okay. So, I am not going to verify this. So, now using this you can see that whenever you have some A power k B, that can be replaced by B A power minus k, but note that this A power n being identity tells you that A inverse must be power of A, which is A power n minus 1, and similarly B square identity tells you that B inverse must be exactly power of B, which is B. Okay. So, these two things are there. So, now combining these two we can see that A power k B is nothing but B A inverse power k, which is nothing but B A power k into n minus 1. Okay. So, now if you use division algorithm and then write k n minus 1 as something, okay, modulo n. So, then that power is going to come here. Okay. So, if you think about it, so this is going to be exactly n minus k. And note that if you take k from 0 to n minus 1, then this n minus k is going to be non-negative. So, n minus k is going to be non-negative. So, then this is exactly a power k b is exactly b a power n minus k. Okay. So, this is what this identity says for k from 0 to n minus 1. So, now we have all these relations. So, now let us go back to the group and then see what other conditions are there. There is this one more condition, G is generated by this AB. So, now you can see that since G is generated by AB, so given any typical element X will look like X equal to some A1, A2 etc. some AR, where AI will come from either A inverse, B inverse. So, that means this AI will come from A some power of A which is n minus 1 again B, okay, because B equal to B inverse. So, that means this X you can write it as some A power K1 B power K2, A power K3 B K power 3 and so on, some A power KR B power KR plus 1. And these KIs can be just non-negative integer, okay, non-negative integers, because X is written as product of all these AIs, where AIs comes from this. So, now using this relation you can see that whenever you see A power KB, you are allowed to replace that by B power A power n minus k. So, that means whenever it is not in the correct order, so we want to write it in the correct order, okay. So, we claim that, okay, let us make a claim first. So, claim is that the group is given by A power k B power L, where 0 less than or equal to k less than or equal to n minus 1 and 0 less than or equal to L less than or equal to 1. So, now we may not know that whether A power k B power L could be equal to some other tuple A power k dash B power L dash. So, it can potentially can have less number of elements, but from this claim it is immediate that the cardinality of G is at most 2n. So, that is all we wanted. Okay. So, that is the claim that we are making, and that is clear from this claim. So, now given X, we already know that it can be written as some A power K1 B power K2 etc. A power some KR B power KR plus 1. Okay. So, now you can see that if something is not in the correct order, okay, so you are allowed to actually replace. So, let us rewrite that relation, that is B A power n minus k, B A power n minus k is nothing but A power k B. If B power is 0, then it is all going to add up. This K2 is 0, then it will, then K1 and K3 will add up, okay, that will be in the correct order. So, the only time when Ki or K2 is 1, so that is the time you will be having power 1 here. So, that time you can switch. So, now just use induction and convince yourself, use induction, convince yourself that X is some A power K dash B power R dash. Now, K dash has to be between 0 to n minus 1, because A power n is identity, there is no other option, and R dash also can be at most 0 or 1, there is no other option. So, that proves that G is indeed equal to this A power k B power L, where k ranges from 0 to n minus 1 and L ranges from 0 to 1. So, that proves that the cardinality of G can be at most to 2n. Now for some reason, if you know all these products a power k, b power l, all of them are distinct, so then we get G is exactly having 2 power n elements. In that case, you can prove that G is indeed isomorphic to your dihedral group D2n. Okay. So, I will leave it as exercise. If G has 2n additionally, so then prove that G is isomorphic to D2. So, basically this isomorphism comes from mapping A to R and rho to B. Okay. You can directly check because we have this relation B into A power n minus k is same as A power k b. Using that you can check that this map is well defined as well as it is actually group homomorphism. Because they have both same cardinality, it must be bijective, that is not something very difficult to check. Okay. So, I will leave it to you to check, it is okay. Okay. So, now let us focus on finite subgroups of O of R2. So, we want to understand finite subgroups of O of R2. Okay. Let us see what we can do about this. So, we already have two such subgroups. One is cyclic subgroup generated by some rotations. For example, you can take 2 pi by n, okay, counterclockwise rotation generated by this 2 pi by n, and then take subgroup generated by this. So, this is going to be cyclic group of order n, and this naturally sits inside O of R2. This is something we have seen. We have just seen that this D2n naturally sits inside this O of R2. So, this is the dihedral group of order 2n. So, now we want to ask the question, are there any other finite subgroups of O of R2? So, our claim is, so here is the theorem. So, these are all the only. Okay. If G is a finite subgroup of O of R2, then G is isomorphic to, let us call this is some Cn or this is D2n. Okay. So, these are all the only finite subgroups of O of R2. Okay. So, let us see how one can prove this. Let us start with G. Okay. Let us say G is a subgroup of O of R2, which is a finite subgroup. Okay. So, now note that you have this determinant map from O of R2 to plus or minus 1, okay, because all the elements in O of R2, they are all linear maps that fixes origin. So, they are isometries that fixes origin. So, that must have determinant plus or minus 1, that is what we saw. So, now you can see that you can restrict this determinant map to G. So, again you will get a group homomorphism from G to plus or minus 1. Now, you take H to be the kernel of this map, determinant restricted to G. So, now there are two choices, either H is full or it is proper. So, let us actually first understand this H. So, what is this H? If I start with some T from this H, then the determinant of that is 1. That means this T is nothing but some rotation or theta of T. In the matrix form, you can see that this is going to be cosine theta of T, sin theta of T, and then minus sin theta of T, cosine theta of T. So, this is something we have already observed. Okay. If you start with an element of this O of R2, if it has determinant 1, then that must be a rotation, okay, and rotation about the origin. And if it has determinant minus 1, that must be reflection, and we also have formula for that. So, now this is a rotation with respect to let us say theta of t. So, now we want to understand this h. Okay, what we will do? We will actually choose r. Okay, you choose r inside h such that this theta of r is as minimum as possible. So, why one can choose such theta of r? Because each element of h is uniquely determined by its the angle, because it is a rotation by some angle, that we are calling it theta of t, and h is a finite set. So, there are only finitely many angles. So, you can choose the minimum among them. Now, our claim is h must be generated by this r. So, this is our claim. If we prove this, then we are almost done, because h becomes cyclic subgroup of this G. Then using h you can conclude something about G. But let us see that how one can prove it is actually cyclic. So, you start with another t in h, and then you want to prove that t must be some r power n. So, it is very similar to the argument that you say that subgroup of a cyclic group is cyclic. So, now given this t, what you do? You choose some natural number m greater than or equal to n, such that m times this theta of r is less than or equal to theta of t strictly less than m plus 1 theta of r. Okay. So, such m exists because theta of r is less than or equal to theta of t. You choose minimum m such that theta of t is actually greater than or equal to that m times theta of r, then you will actually get this. Sorry, m theta of r is less than or equal to theta of t, then you will get such m. Okay. So, now how do you use this m? So, you can see that if you compute this theta of r minus some t, okay, this is, see, r is rotation. So, r inverse is rotation, any power of r is rotation, t is also a rotation, both are rotation about origin. So, composition of this rotation again going to be rotation. Okay. So, then what will be the angle? So, the angle will just add up. So, if theta of r is the angle for r, then minus theta of r will be the angle for r power minus 1. Then r power minus m will have angle minus m times theta of r. So, the angle of this will be theta of t minus m times theta of r. So, this will be the angle. But note that this is going to be greater than or equal to 0 and strictly less than theta of r. Okay. But theta of r is the minimal possible angle. So, this is the non-zero angle because this corresponds to your rotation. Choose a rotation that has this minimum angle. So, that must be non-identity map. So, that means this theta of r is non-zero, that forces that this element r power minus some t cannot be just a rotation, it has to be identity. So, then that means this r power minus some t is identity, that means t is r power m. So, this proves this h is generated by r power m. Okay. The h is generated by r. So, now go to G and then try to understand how one can actually relate this G with h. But before that, let us understand h alone. Okay. H is, now we know that it is generated by r, and r corresponds to the clockwise rotation r of theta of t. But since h is a finite group, let us say r of h is n. So, then r power n must be identity. Since r generates, so the order of r also should be n. So, that means the theta of t is forced to be 2 pi by n. There is no other option, because r power n must be identity. Okay. But r is nothing but what? Cosine theta of t, sin theta of t, minus sin theta of t, cosine theta of t. So, now if you raise it power n here, then you can see that. So, this is going to give you exactly n here, n here, n here, n. Okay. So, then you can see that you need to have this e power I n times theta of t is equal to 1. So, that would tell you that theta of r, everywhere it is r. So, theta of r should be just 2 pi by n, because n times theta of, so theta of t already lies, theta of r lies in between 2 pi and 0. Okay, this is just some simple fact from complex analysis. I guess you can do this. So, this proves that what is your r? R is nothing but r 2 pi by n. So, this is your rotation about the origin, okay, and h is very explicitly given by this particular cyclic subgroup generated by this rotation by 2 pi by n. So, now you can see that h is nothing but the kernel of determinant. So, that h is a normal subgroup of G. So, now since G modulo h is isomorphic to plus or minus 1, as okay, if h is proper in G, okay. So, if h equal to G, then there is nothing to prove, okay, then there is nothing to see. So, that means this G is isomorphic to the cycle group Cn. So, now we want to assume h is not equal to G. In that case, you have G modulo h is isomorphic to plus or minus 1. So, that means the cardinality of G is 2 times the cardinality of h, which is 2 times n. Now, if you choose some s from G, which is a reflection. So, reflection means the determinant of s is minus 1, then you can see that G is nothing but h disjoint union s times h. So, that means the G has to be equal to r power k, okay. You can also see that sh will be same as hs, as h has index 2, okay, the G modulo h is 2. So, then this is r power k, s power l, and then k varying from 0 to n, and then l is varying from 0 to 1, okay. So, basically G has exactly 2n number of elements, and G is given very explicitly by these elements. So, now it is easy exercise to prove that this D2n is isomorphic to your G, okay. You send our R to R and then rho to S, okay. So, that will be your isomorphism. But if you want to, if you are really interested in identifying G as symmetries of some n-gon, so what we need to do, so we need to actually fix this reflection S, okay. So, then you can easily see that since G is subgroup of this O of R2, each element of G is going to leave S1 invariant, okay. So, in particularly this S also going to leave S1 invariant. So, now you draw this circle, okay. So, now what you do, you just pick this line which actually fixed by this S. So, this is L. So, S is a reflection with respect to the line L, okay. So, now you can see that if you pick a point on this, okay, so call that as vertex 1, then this S of V1 is V1, okay. So, now what we can do, you want to apply G on V1 and then see what happens, each element of G. So, this is G on V1 where G is coming from G. So, now you can see that this is going to be R power k V1 where k varies from 0 to n minus 1. Why? Because S fixes, so S square also fixes, no issue. So, but G is given by all these elements R power k, S power L. So, that means these are all the only points that you get, but exactly how many points you are getting? You are getting exactly n points, because the rotation fixes only the origin. it can fix it has only one fixed point, it cannot fix anything else. So, this rotation R has to take V1 to different points. Okay. So, that means, so this is going to map some V2, this is going to be your R V1 and so on, and then you will come to R power n minus 1 V1, which is going to be your Vn. So, this is the n-gon that you will be getting. Okay. Now, it is clear that your group G actually leaves this n-gon invariant, and the symmetries of this n-gon is going to be exactly your G, because it will have exactly 2n number of elements, and these are all the elements that you have already listed. So, they are all distinct elements. Why they are all distinct elements? Because, so like I said, if you make them equal, then it will say that rotation equal to reflection, that cannot happen. So, that means they are all distinct. So, anyway, so this shows that you have a natural n-gon, okay, for this group G, on which it is naturally acting, okay, and then you can see that the symmetries of that n-gon is nothing but your group G. So, this is also telling you that you are allowed to actually change this n-gon, there is no issue, okay, because this reflection, yes, is randomly chosen reflection. You can also choose some other reflection and then try to play around the same game. Okay. So, I will leave it you to think about all this, like what are all the possible points, that what are all the possible n-gons that you will be able to get it from this argument. Okay. Okay, I will actually stop here. So, this is actually completes all the results about actually isometries. So, we understood what are all the isometries of R2, and then later we defined the dihedral group, and then we realized that the finite subgroups of this O of R2, they are nothing but either cyclic group or this dihedral groups. Okay. So, with this actually we actually get lots of examples coming from this isometries. Okay. So, I will stop here. Thank you.